Okay, so one of the first results that people will typically prove in linear algebra or functional analysis is the existence of an orthonormal basis. In the case of a finite dimensional space, the trick that you use to prove the existence of an orthonormal basis is you use something called the Gram-Schmidt process. So the first question that maybe the first approach you would use to try to generate an orthonormal basis in the context of an indefinite space is to use Gram-Schmidt. But if you look at Gram-Schmidt, you run into a problem, which is that in Gram-Schmidt, one of the steps is that you divide by the inner square of a vector. And we know that sometimes the inner square can be 0. So Gram-Schmidt as it is doesn't immediately work. So we have to do a little bit more work in order to prove the existence of orthonormal bases. And that's basically what I'm going to try to do today. Yeah. So here's some things that we have from basic linear algebra that are going to be helpful. A basis is something that we try to use to decompose a space as a direct sum of simpler spaces. In this case, so the basis elements would span like a one-dimensional space, and we write our big space as a direct sum of the smaller spaces. All right, so first I'm going to define what a direct sum is. So if I give you, let's say, okay, so V and W are vector spaces. We will say that V is a direct summand. Oh, wait, sorry, I forgot. I need to write these bigger so that you guys on Zoom can see them. Okay, if there exists another subspace, maybe I'll call this one U. So V is another subspace in W, such that you intersect the other subspace as 0, and additionally, if you form the space generated by adding all the vectors in V and adding all the vectors in U, then you get the entire space. In this case, we say that V would be a complementary subspace U. And instead of writing all of this every time, we can use the shorthand notation, which is that W is U plus V, but with this dot above it. So this notation basically means all of this. Okay, so that's the first thing that we'll use to try to get a basis. The next thing is, so I'm talking about orthogonal bases, and I need to define what the word orthogonal means. So, okay, now let's say that, W is an inner product space. So we will equip it with some inner product, actually indefinite. I will say that two vectors in W are orthogonal, and we use this shorthand notation for that, if and only if the W equals 0. If I give you some subset of vectors, which is not necessarily a subspace, we define the orthogonal complement as the set of all, let's say, V and W, such that SV has vanishing inner product. Sorry, for all S and S. And then maybe one of the tricks that Jean Bernard taught me is that if you ever have a set that's defined by some criteria that holds for a bunch of stuff, you could write it as this intersection instead. And I mean, this is maybe a tangent. This trick isn't going to be extremely useful, but for today. But generally, writing sets in this way lets you prove things like maybe the set is closed in a way that would be easier than if you didn't write it like this. Okay. So let's see. Here's some fun facts about the orthogonal complement. Okay, so our first fact is that so if I give you one set that's a subset of another set, then uh, the orthogonal complement reverses the order of the subset. If you wanted to be precise, you could say that orthogonal complementation is an anti-isotone map on the ordered set that is the power set of all subsets of the vector space. Okay, next fact. Uh, so even if S is not necessarily a subspace itself, the orthogonal complement is always a subspace. Which means that it's closed under the rescaling and addition operations on the vector space. Okay. Now, if I give you two subsets, let's say S and T, the natural vector space operations that we like to use are set intersection. And so if I take the orthogonal complement of this, turns out that this is equivalent to these spaces. And in fact, this just follows from that. If you start by proving the first two facts, you get this thing immediately. The next fun fact is this. And then our third fun fact has to do with taking the orthogonal complement twice. There's perhaps a thing you can do like called an orthogonal closure, that if you take the orthogonal complement twice, you get something bigger than where you started. Okay, so these all just follow immediately from the definition of orthogonality, and these are things that you're likely familiar with from traditional linear algebra functional analysis. Right, so now I have direct sums and I have orthogonality. So then the next thing I might want is an orthogonal direct sum. So an orthogonal direct sum is one like this. So the subspaces are orthogonal to each other, and if this happens, we'll use a different notation. I'm going to put this direct sum symbol in the brackets. So this means that W is a orthogonal direct sum of the subspaces. Okay. So now is a good time for an example. So we can consider perhaps a canonical example of an indefinite interproduct space, which I gave last time, which is the indefinite inner product space whose gram matrix is the SIP matrix. So I can give you Fn with the standard involuntary permutation matrix. And as a reminder, this is defined as follows, that P of I E n minus I plus 1. So then what I can do is, okay, maybe the simplest subset I can have is, I mean, a simple subset is this one, just a set consisting of only the first basis vector. And the orthogonal complement of this would be the linear space, which is the span J, where J lives in n minus 1. And so the first thing that perhaps you'll notice here, that's a big difference between orthogonal companions for definite inner product spaces versus indefinite inner product spaces, is that this orthogonal companion is not a complementary subspace to what you started with. So to be more explicit, if I call this, let's say V, then this statement is not true. And so one thing that perhaps you'll recall so in traditional functional analysis, we have the Hilbert projection theorem. And a corollary of this theorem is that if I give you a closed linear subspace of the Hilbert space, so this is closed and linear, then I can decompose the Hilbert space as a direct sum. So there's a question of, so there's this classical result from linear algebra that clearly doesn't hold in general for the indefinite case. So there's a question we can ask, which is, well, what went wrong? So the answer to what went wrong is that this vector space has a non-trivial intersection with its orthogonal companion. So if we look here in our example, the basis vector E0 lives in both this subspace and its orthogonal companion. So I have kind of this double counting of vectors, which is why I wasn't able to get the entire space. So basically what I'd like to do next is, yep.
You don't have the decomposition like this, but do you still have the dimension equality?
Yes. Yeah, so you still have the dimension of equality. I will explicitly establish this shortly. But don't spoil it. So if I want to attach some verbiage to this statement, what I can do is I can say that this thing, I can call it the isotropic part of V. And I can denote it as this. Now, the book that I was reading had, they called it V superscript 0, but I had this whole rant last time about why you should understand superscripts as cardinal exponentiation of sets. So to not overload the superscript symbol, just gonna put the superscript to the left. And then what we'll do is we will say, okay, so V here, this is a, okay, so V is a subspace of W still. If there exist non-trivial isotropic vectors in V, then we will call V degenerate. We'll call it non-degenerate otherwise. So basically the idea is that all of these orthogonal decompositions of spaces have something to, their existence has something to do with the non-degeneracy of their constituents. So I'm going to establish this. Okay, so as a first step to relating the non-degeneracy of a subspace to its ability to be a direct summand, I'll just prove a quick lemma regarding the isotropic parts of direct summands, and that's this one. So I can either compute the isotropic part of a direct sum after doing the direct sum, or I can compute the isotropic parts first and then compute a direct sum. So this is a lemma. Okay, so basically I can complete the proof in 3 stages. So I can get rid of all the extra baggage on this plus symbol. So I can first prove that the statement works if I get rid of the baggage. And then I can upgrade the statement so that it has the baggage, so that the sum becomes a direct sum, and then it's an orthogonal sum. So it's a 3-step piece. I'll do the hardest one first. We eat our vegetables first in this family. So so by definition, this is equal to this. And then something that's kind of miraculous for linear subspaces is that the set of all linear subspaces is a ring. It's a ring when equipped with the addition operation of plus and the multiplication operation of intersection. And then you can go on and establish that the 0 element of the ring is the trivial subspace that has only the 0 vector. You can show that the unit of the ring is the entire space. Those aren't extremely necessary, but the point I want to say is that in a ring we have the distributive law. So this set intersection, it turns out to distribute over set addition. Okay, so this is something that you can prove separately. I won't do it here. So because of the distributive law, we have this. Okay, so I multiplied this in here. Now I'll add it here. Okay, so then the next thing I can do is maybe I shouldn't have erased my fun facts for this sum, but one of them let me replace the orthogonal complement of a sum of subspaces with the intersection of the orthogonal complements. So that's the next step. Write it like this. And set intersection is associative, so I can drop parentheses. Okay. So I know that I said I would first prove the set addition property without the baggage, but I already know in advance that because I wrote this funny looking combination, I know that this subspace is orthogonal to this subspace. This whole thing was an abbreviation that had one of those terms and conditions in there. So because I know that this is orthogonal to this, I know that U is a subset of the orthogonal complement of V. And that lets me simplify this set intersection to U. Somehow I lost an orthogonal complement symbol over here. And then by definition of the isotropic part, this is 0U plus 0V. Okay, so this is the first step to the proof of this. Now the next two steps are easier, I promised. Let's see, so what else do we need? We need that the intersection of these two guys is trivial. And I mean, that's pretty straightforward because we know that by definition, the isotropic part is a subset, and we know that the isotropic part V is a subset. Therefore, their intersection is a subset of the intersection of U and V, which is just the zero vector by supposition. So we get that for free. And then the last part is we can use one of the other fun facts that I conveniently erased, which is, so we know that this is true. Therefore, we have, let me do it like this. So U is contained in the orthogonal complement of V, and this is contained in this, because the orthogonal complement is this anti-isotone map. So then if you want, you could just ignore this part now, maybe a black box that I use to establish that the isotropic part of U is contained in the orthogonal complement of the isotropic part of V. Okay, so this proves this lemma. Okay, so why did I establish this lemma? There's a corollary that fits into the story of orthogonal bases. So the corollary is this. So let's say that W is our big space, and the big space is non-degenerate. If this is true, let's see, then if, let's see, how do I say this? I think I forgot to define a word. So I talked about complementary subspaces. So if I have this, so if it was just the big space is a direct sum of two subspaces, I would call them complementary to each other. But if this is true, I would call this the ortho complement of E. And if our subspace U is sufficiently nice so that it has an ortho complement, then we would say that U is ortho complemented. Okay, so where was I originally going? That a non-degenerate in a non-degenerate space, if a subspace is ortho-complemented, space. So if a subspace is ortho-complemented, then L is non-degenerate. And so is its ortho-complement. Okay, so the way to see the corollary is pretty straightforward. So W is non-degenerate, which means that the isotropic part consists of only the zero vector. So I have 0 but by definition of orthocomplementation, this space W is equivalent to the orthogonal direct sum of, I guess, maybe to be consistent, I can go back to calling it U. But because of the lemma, we have this relationship. And the only way for this relationship to be true is if the isotropic parts of both the subspace and its orthocomplement are just the zero vector. If either of these was bigger, this space would be bigger. So basically, this corollary is establishing that the problem that we saw in the previous example, which we had a subspace that had an isotropic part, this is somehow generic. That if I ever give you a subspace that's non-degenerate, or no, if I ever give you a subspace that is degenerate, then it's not orthocomplemented. So this is one direction of the proof. And you'll note that I made very little assumptions regarding the global space. I didn't put any topology on it. So for example, when I talked about the Hilbert projection theorem, I had to talk about closed subspaces, so I didn't do any of that here. The price I have to pay for not doing all that extra stuff is that I only get one direction of this proof. So this statement is just an implication that if something is orthocomplemented, then it's non-degenerate, but I don't get it the other way. I don't get to say that every non-degenerate subspace is orthocomplement. So because I haven't talked too much about the topological structure of these guys yet, it's difficult to make if and only if statements. However, the simple case that you can end up in is the finite dimensional case, where kind of the topological considerations are trivial in some sense. You just have the Euclidean topology. So what I can do is show that this implication is an equivalence in the finite dimensional case. And so to do that, I'm going to prove the equality that you suggested earlier. Okay. This is the lemma. And so because I'm I don't know if lazy is the right term, but so when I consider the dimension of a space, for now, I'm just going to let it either be a finite number or some symbol that I call infinity. And because I want to be precise, I'll say that it's either aleph null or whatever the dimension of the space is. And I don't really know how to write the symbol aleph very well, so I'm going to use this curly script n. And if you guys have a suggestion for a better way to write it, now would be the time to share it. And if not, we're going to use curly n. So this will either be this symbol, or it'll just equal the dimension of the if the is finite dimensional. Okay, so this is the thing I want to prove. That let's see. So I'm going to give you two subspaces of an inner product space. So this statement is perhaps a little bit stronger than what you suggested in words, because this is a statement regarding two subspaces rather than just a subspace and its orthogonal complement. Okay, so for the proof, the first thing that you'll notice is that this inequality trivially holds if M is infinite dimensional, because it's already the biggest thing it can be. So the biggest thing is going to be greater than everything else. So without loss of generality, I can assume that this is going to be finite dimensional. And then the next thing I can do is, without loss of generality, I can suppose that this, the dimension of the subspace L, is going to be greater than the dimension of the subspace M. Because in the other case, the inequality is also trivially true. Because this is a positive, a non-zero number. Okay, so we can assume that and this is a natural. So at this step, what we can do is we can construct, because I assume this is finite dimensional, that means there exists a basis. So let's let that basis, I'll give it a name, I'm going to call it F, because I wanted to reserve E for the basis of this guy, and F is the next letter in the alphabet, as M comes after L. So I'm going to call it F. And I'm going to give that basis an enumeration. So I can just label the stuff in it. It's possible that maybe we can rewrite the proof without the enumeration, but this is the way I did it at first. Okay. And then what I can do is I can consider a finite dimensional subspace of this guy with dimension, let's say, little l. So a finite dimensional subspace would be something that is generated by a map equivalent to this one. So I'll say there exists an enumeration of the basis that goes from here to Gen L, such that This is linearly independent. One last thing I'll note is, so the other day when I was giving this rant about why you should be using the set theoretic construction of natural numbers because it simplifies a lot of expressions. You have to be careful when referring to the image of a function. So here I'm referring to the image with square brackets. If you overload the image symbol by using parentheses, you run into a potential notation clash, because is this the application of a function to the element L, or is it the image of this set? So if you're gonna be abusing the set theoretic definition of natural numbers, you really should change the notation that you use for the image of a function to square brackets. Okay, so then what we can do is talk about this guy. So I can say that the vector x is in that piece. So actually, I'll just talk about a subset. I'll talk about the subset that's generated by this map. So this will be image E of L, and I have to take the span so that I get a vector space. Span. So a vector lives in that guy, if and only if. So first, it emits an expression in terms of this basis. So we'll say there exists alpha in the set of L tuples over the ground field, such that x is the sum like this, and for it to live in the orthogonal complement of the other subspace, so I came up with this basis. So what that means is that this inner product, so f, let's say fk equals 0, all k in dim m. And so basically these, you can expand these in terms of the tuples. And what this amounts to is dim m linear equations for L unknowns. So the set of all of these potential unknowns is at least L minus m dimensional. And so this statement, basically, if you massage it, you get back to the inequality we're looking for. And so this little m, I didn't define it, sorry. So this is dim m. The dimension of this set of all alpha is equivalent to the dimension of the intersection of the orthogonal complement of m with the span of the basis E I came up with. So we have dim L intersect m perp greater than or equal to the dimension, the span, image, intersect m perp. and we know that this is greater than or equal to L minus dim M. So if you just add dim M to both sides, then I know that this quantity is greater than or equal to some L for all L that's less than or equal to dim L. So then if you take a supremum over both sides, then you get the desired inequality. Okay. This is something that's true. And so the special case is we can get an inequality for just one subspace rather than two. So I can set L to be my entire space, which I guess I call V there, in which case this reduces to this. Now here, because I haven't made any non-degeneracy assumptions on the subspace, it's entirely possible that this inequality is actually an inequality rather than an equality. The trivial case would be, for example, if I had the completely neutral inner product, the inner product, which is the function that just maps everything into zero. If you have that, then the orthogonal complement of any subspace is the entire space. So this is actually an inequality sometimes, not just straight up an equality. However, what we can do is show that in the non-degenerate case, that it becomes an equality, because in the non-degenerate case, we have, let's say, degenerate. That means that so if I have this, then I can construct the subspace M perp plus M. This is going to be a linear subspace, assuming that M is a linear subspace. So this is contained in V. And the dimension of this would be the sum of the dimension of the constituents, specifically because of this linear independence constraint. So what that means is that if M is non-degenerate, well, first of all, we have as the dimension M perp plus dimension of M equals the dimension of V. And then perhaps more strikingly, we have M plus M perp equals V. So now, because this subspace is orthogonal to this subspace, and their intersection is zero, I can go ahead and use the orthogonal direct sum notation. So V would be M orthogonal direct sum M perp. And so by doing this, what I've established is an equivalence. So if W is finite dimensional, and non-degenerate, then we have W equals, I don't know why I keep changing letters all the time, so forgive me. So I can decompose this as an orthogonal direct sum if and only if the subspace is non-degenerate. Okay. Do you have any questions? So now the next thing is, because I can construct this orthogonal direct sum of a subspace with its orthogonal complement, the trick to getting to what we were originally after, which is the existence of orthonormal bases, we're going to construct an orthonormal bases for non-degenerate spaces one step at a time, using this. Okay, so what do I mean by that? First, I'll just clarify that when I say the word orthonormal basis, that we're both talking about the same thing. Definition, basis, let's say B in an inner product space V is an orthonormal basis, which we'll abbreviate as ONB. If and only if for every pair of basis vectors B and B prime, we have this inner product is equal to 1 or 0. 1 if B is equal to B prime, and 0 if B is not equal to B prime. And one of the things you'll notice in my definition of orthonormal basis is that I had to put these absolute value bars here. If you wanted to drop them, it could be possible that one of your basis elements is a negative vector. And so in here, you would just have to say that if B is B prime, it's either 1 or -1. However, because the inner square of a vector is always a real number, you wouldn't have to worry about this being like e to the I theta or something else that's on the unit circle in the complex plane. Okay, so this is an orthonormal basis. And so now our task is to try to construct an orthonormal basis. And we're going to do it just for the non-degenerate case, because in the non-degenerate case, I have this very powerful kid. Okay. So if W is non-degenerate, so the first thing that I'm going to do is I'm going to pick a vector in here that is not neutral. If every vector is neutral in the space, we can prove that it's degenerate. So maybe this is a lemma, but so the first step to constructing an orthonormal basis is to pick one non-neutral vector. Okay, so the lemma is that if W is non-degenerate, there exists a vector which is not neutral, which means that the inner square is non-zero. And so the proof of that relies on the polarization identity, which says that I can take an inner product between any two vectors, V and W, and express it as a sum of pieces that have inner squares. So I'll just write it in the complex case, but in the real case, it's the same concept. So if this is 0 for every vector in the space, that means the right-hand side of this equality is identically 0. And so if this is 0 for all VV, what that means is that, so W is some vector in my vector space that's orthogonal to every V in the vector space, which would mean that it's an isotropic vector, which would mean that W is degenerate. Okay, so that's maybe the first lemma. There exists a non-neutral vector. And so this is the starting point to find our orthonormal basis, because look at the requirement. The requirement is that the elements of the orthonormal basis have to be non-neutral. So that's the first step. The next step So I can construct the subspace, which is the span of, I think this is going to be more clear if I phrase this as an inductive argument. Basically, what I'm going to do is reduce the problem of constructing an orthonormal basis for, let's say, an n-dimensional space to an n-1 dimensional space. So if I rephrase this as the theorem that I prove with induction, that should be perhaps more clear. Okay, so theorem. Every non-degenerate space, W, so a non-degenerate space is one such that the only isotropic vectors are 0, has an orthonormal basis. And where W is finite dimensional. Okay, so if I'm going to prove it with induction, the first thing I do is a base case. So there are no zero-dimensional non-degenerate spaces because a zero-dimensional space is just a zero vector, which we know is not non-degenerate. It's zero is a neutral vector. So the base case is going to have to be a one-dimensional space. And in this one-dimensional space, again, there exists a non-neutral vector, which is just the one that spans it. So we'll just say that, let's say V in W is non-neutral if the dimension is 1. So our orthonormal basis is simply, maybe I'll give the basis a name, I'll call it B. This is just the span, our basis vector is just V over its inner square. And then we may have to do something funny to normalize it, like take the absolute value and a square root. That's the base case. The inductive hypothesis is that we've established that every n-dimensional non-degenerate space has an orthonormal basis. So we're going to start with the statement being true at dim W equals 1. Or let's say it's true statement. So this is true for all spaces with dimension m, which are less than n. And now we need to prove it for n. So if I give you an n-dimensional space where n is going to be greater than 1 now, because I already proved the one-dimensional space case, what we can do is I can give you a non-neutral vector such that this is non-neutral. So this exists. And so then what I can do is I can write W as the direct sum of the span of this vector. Because again, we now know that this is non-degenerate. The span, we can take the orthogonal direct sum with its orthogonal complement. So if this thing is n-dimensional, this guy is n-1 dimensional. So what that means is that by the inductive hypothesis, that This has a basis. We'll call it B tilde, which is orthonormal. And then we can say that the basis that we're looking for is B tilde, along with the non-neutral vector that we used to start the proof with. So this with the non-neutral vector, and we normalize it. So this is an orthonormal basis. So if you will, you could consider this like an analog of the Gram-Schmidt procedure that works for non-degenerate finite dimensional inner product spaces. And the important thing is that at every step along the way, I have a non-neutral vector. All right, it's been about an hour. We can take a brief break now. I guess I can start again in 5 minutes.
Going there was a nightmare. Yeah, they lost my dosage. And so I mean I got it the same day, but I arrived at like 1 in the afternoon at the airport of Rome, and then I get a bus like at 6. What happened is that I arrived and I had my luggage. It was not lost, it was delayed. And so I come to the test of the journey. I should arrive this day. So and I say, in any case, I have to wait 6, so I will wait here. So I wait, but in the end, I mean, I come back. I mean, they told me before 6. They told me, okay, so the plane is delayed. My bus is leaving. They start to say, yeah, you can. I mean, it is on the plane. It will come. So just give us the address of your hotel, and we will deliver it to you in like. It was a Saturday, so Sunday now, and then 2 days after Sunday. I said, but I don't care. I mean, I went specifically on the Saturday because there was an activity in the mountain on Saturday, and I had all my clothes for the activity on the luggage. I said, and so then I changed the bus like 3 hours after, so I had to wait 3 hours more. My luggage arrived, and I arrived in La Quilla at 1 in the night. Oh my God. And 3 kilometers away from the hotel. And so I said, no problem, I'm in the university paid. Uber. No, nobody available. And it is very difficult to walk your pavement on the street, and you have to climb. I mean, climb. I don't want to come back to L'Aquila, but really to come back. I mean, no specific problem. I mean, everything is usual, but still, you're forced to take like 2 hours and a half on bus, and then the plane to Madrid, and then change plane. And there is no Bilbao Rome directly. So
There is
it's
Bilbao Rome.
really long. No, I mean, every like once a week. I think there's a reason, but yeah. I mean, someone told me to look at that, but I didn't think of that. So yeah, I mean, it is really. I mean, to come back, I left the hotel at 5, and I arrived here at 6 in the afternoon. I mean, 13 hours, and everything was. I mean, with no problem. Everything is normal. It's the time. So yeah, I don't want to. I don't know why they put it in this place. Instead of nowhere.
I guess it's nice, no? At least it's.
I mean, the city is in construction, and they are rebuilding everything. But it's nice. It's nice, but I don't really, I mean, it's more like, don't really understand the question.
Was Volker there or the
No.
the students there?
And no, the students,
Also, no?
there were a lot of German, like not the German from False point.
How was your presentation there?
Good, but
Yeah,
really short.
Valentine.
It was just 10 minutes, so that's, but yeah, I had some question and I had to have into break people. I guess it's a good. There is something in Milan in fact, a conference in Milan better in May, but and I don't want to travel just bring before statistics. I talk about that. But Milan is better. I think there is below Milan direct page by
Yeah.
and then you have to focus on this and so on.
Did you ever go to Italy, Jacob?
I've been there a few times.
Yeah. In which cities?
I was in Palermo, I think, not last summer, but the summer before.
For a conference?
That time for a conference, yes.
I remember, I checked the conference, maybe it was about, what was it about? Do you remember?
Like C-star algebras,
Mm.
and I mean, kind of a broad, well, okay, I think the formal title was like functional analysis and quantum physics.
Nice.
But everyone was talking about C-star algebras.
Nice.
Okay. Okay, so there's a couple things I wanted to do next. So the first is we had this statement regarding the existence of orthocomplements, which holds in the case where the total space is finite dimensional. And okay, so I still haven't introduced any topology yet, but this statement can be upgraded even without it, where instead of assuming that the global space is finite dimensional, you just assume that the subspace that you're trying to find the orthogonal complement of is finite dimensional. So this can be upgraded a little bit. The other thing I wanted to do was establish the utility of orthonormal bases. And so first of all, I'll mention that I have to actually use an orthonormal basis of the subspace in order to prove the more general statement. So that's one place where this is used. Another thing that you can do is you can have a so-called resolution of identity using an orthonormal basis. And so that kind of carries through the same way that it does in the definite case. So we have a resolution of identity, and then the resolution of identity, if you look at the terms in it, you get a Parseval identity as well. Okay. So, okay, where do we start? Okay, so the resolution of identity is as follows. Say that for every V in some inner product space, that's finite dimensional. So if finite dimensional and non-degenerate. we can express this vector as a sum. Well, okay, hang on. Let's say let B be an orthonormal basis, which we know exists. And so to prove this formula, so actually, I guess maybe I can give this a name. I can call this vector v prime for every v, and our goal is to show that v prime is equal to v. So to show that v prime is equal to v, what I'm going to do is say that because we know the space is non-degenerate, we know that 0 is the only vector that's orthogonal to everything else in the space. And then I'm going to try to construct 0. I'm going to construct 0 by taking a difference between v prime and v. So our objective is to show that v prime minus v with w is 0 for all w. Okay, so to do that, we can write this as, okay, let's see. So we can use this Hessel linearity property to pull out the minus VW part. And maybe I'll do the sum this way, just to simplify the next line. So this will be VW minus, now V prime I sub in the definition. Okay, now from the definition, again, by the linearity property, I can pull this guy out. And because I'm using the physicist convention that this is linear in the second argument, I have to conjugate this constant factor. This denominator is real, so that doesn't matter. So this will be minus a sum. So here I pulled out the scalars. Okay, I'm pausing because I realized that the original proof that I had was circular. Because at this point, what I wanted to do was say that I could take this and then move it into W and rewrite that thing as W, but that requires circular logic. So let me prepare something on this for next time. This is a true statement. So then the next thing that the parsable identity gives us is that we can compute the inner square of a vector v with itself by using these coefficients. And so we can verify that this is equal to this. So this is the parsable identity. All right, let's see. The next thing I wanted to do was generalize this statement to a case where the global space is infinite dimensional, but the subspace is finite dimensional. To do that, as I've done so far with basically everything I wanted to prove, I prove a lemma first, and then the lemma makes the proof of the actual thing easy. And in this case, the lemma I'm going to try to show is that I'm going to give an equivalent characterization for the statement that a subspace is orthocomplemented. I'm going to give this using a so-called orthogonal projection. Okay, so this is maybe proposition. And in order to define what I mean by an orthogonal projection, I'm going to actually introduce what a self-adjoint operator is now. Definition. So P being linear is, I guess, symmetric. If and only if we have V P W, V W for all V and W. Now there's a difference between the definition of a symmetric and a self-adjoint operator, which effectively has something to do with the domain of an adjoint, and I haven't really defined an adjoint yet, so I'll just work with I'll use the term symmetric instead of self-adjoint, and those terms are synonymous in the finite dimensional case, which is kind of what we're working with mostly anyway. So let's see, so proposition. Oh, and another aside, so if the physicists came up with different names for this P. So here, this is just symmetric with respect to some potentially indefinite inner product. The physicists wanted to call it pseudo-Hermitian so that it's distinguished from a Hermitian operator. And so to be a little more precise, the other thing that they require for pseudo-hermiticity is that it is symmetric with respect to a non-degenerate inner product. And then usually the physics literature will work with the explicit construction of an inner product being given by a Graham operator like we had last time. So we can say that if P is self-adjoint, so I haven't really properly defined self-adjoint, but for now, just think it's symmetric with respect to a non-degenerate inner product defined by a Graham operator. So I'll say and the non-degeneracy criteria for an inner product with a Graham operator is that the kernel of G is the zero vector. So if there is an element in the kernel of G, that would be an isotropic vector, which is a problem. So G is some invertible map, and in the finite dimensional case, it's invertible, it's bijective. So if it's self-adjoint with respect to this, we say P is pseudo-Hermitian. And then something that I find rather curious is that this term pseudo-Hermitian was introduced in a paper in the mid-50s by Heisenberg. And whenever someone writes about pseudo-hermiticity, they almost never cite Heisenberg. They cite some papers that come much later as definition of pseudo-hermiticity. So, okay, anyway, so this is a big tangent. The proposition regards the thing in our story, which is necessary and sufficient criteria for a subspace to be orthocomplemented. So a space is orthocomplemented if and only if there exists a projection, which is map that's idempotent. E is symmetric. Let's see, and the last one is that the image of this projection I'll say M and W and this, and again with the requirement that W is non-degenerate. If I have these three things, this is necessary and sufficient criteria for a subspace to be M. Okay. So the proof of that So if we go this way, we assume the existence of the projection. What we can do is, so we can say that W, so for every W and W, I can write it as E of W plus W minus P of W. Then what I can do is I can define L to be the set W in W such that, or wait, let's do it like this, W minus P of W. And this is sort of the orthogonal complement of M. So the idea is that this is M, this is L. So to make sure that this works, we need to verify a couple things. So first of all, the fact that W is L plus M, this is trivial. This follows by definition of L. So now, if we want to prove that this is a direct sum, what we need is that the intersection of these is the zero vector. So to verify that, let's assume that I have little w and m. So if this is true, m is the image of the projector. So that means there exists v in w such that w is p of v. And because so now I think what I can do is say that this is equal to P of V. This is the projection property. And then I can just insert this into here. So I have the W is P of W. Means that W minus P of W is 0. So the only vector in L of this form that's also in M is the 0 vector. So this is verified. And then regarding the orthogonality of these two, that follows from the self-adjointness of the projector. So let's say I gave you, so I had W in M. Let's say I give you V in L. So V we can express as W prime minus PW prime. So now the inner product is W prime minus P of W prime with W. And then by the self-adjointness, this is W prime W. Okay, so first I use the sesquilinearity, then I use the self-adjointness. Now, since W is in the subspace M, which is the image of the projector, this argument has already established that I don't have to apply the projector in this. The W is equal to P of W. Okay, so this part right here, we have now concluded that the subspace M is orthocomplement. So this is one direction of the proof. The other direction, okay, so if the subspace M is orthocomplemented, that means there exists L such that L orthogonal direct sum M is W. Now, one thing that perhaps I could have mentioned earlier, but I can mention now, is that for every W, which is in a direct sum space, there exist unique let's say L in L, or maybe I'll call it U, and V in M, such that W equals U plus V. The way that you establish the uniqueness is by assuming that there exists some other pair that works and showing it's equal to the original. So suppose W is equal to U plus V prime, where U prime is in L, V prime is in M. Then we have 0 is equal to U minus U prime. I can just subtract this from that, plus V minus V prime, which implies that U minus U prime is V prime minus V. Now, the left-hand side is a vector in L. The right-hand side is a vector in M. So by definition of the direct sum, this must be 0 because it's in the intersection of elements. Okay. Let's see. So because these constituent vectors are unique, we can define the projector V, or the projector P on W to equal the piece that's in M, which I call V. And this is well defined. And if you use the same algebraic manipulations that we did over for the other direction of the proof, you can get the self-adjointness, and you can get the fact that P is a projector. So this kind of completes the proof. I've constructed the projector. Okay, so now why was I doing all of this? The reason why is now I'm in a position where I can upgrade this statement. So the upgrade is if W is non-degenerate and V in W satisfies the finite dimensionality constraint, then V is orthocomplemented. And so the proof of this, so V is orthocomplemented if and only if there exists a projector that satisfies those nice properties. And I'll now tell you what the projector is. So I'm going to define PB. So B, this will be an orthonormal basis of V, which we know exists because V is finite dimensional. So because I have the orthonormal basis, that means I can define a projector on W that goes to V as follows. So this projector is sort of algebraically the same thing as the other resolution of identity. And so it's probably the case that by proving that this thing is a self-adjoint projector, that would be equivalent to proving the resolution of identity statement that I stated earlier. So our goal is to show that this P is a okay, so now I'm forced to prove the resolution of identity. Otherwise, this proof doesn't work. So first, that P is self-adjoint. We can expand this. Let's see. So now I can put this inner product into the first argument of this inner product. And I have to reverse the order. And then I can now move these denominators in this sum into the first argument of the inner product. And then this, by definition, is the projector. So I have self-adjointness. Now the projection property. If I apply this thing twice, now I have two sums. Let's say the outer sum is B. And now because we use the orthonormality property of B. So if you expand this inner product, you'll see that you're going to end up with an inner product of B and B prime. That will vanish unless B is equal to B prime. So to be more precise, this is going to be non-zero unless B is equal to B prime. And if it is equal to B of B, if they are equal, then all three of these inner products become inner squares and they're equal to each other. So I get back to where I started. So B is in fact, so this projector is in fact a projector and it's orthogonal. The last step is you need to show that its image is the entire space. Sorry, this way. And so I think the trick to that is showing that we can get all of the basis vectors in V. If we can get all the basis vectors in V, then you can generate all of V. And so I think the way to get all the basis vectors is really straightforward. You should just be able to show this. And so I'm sure you can go through and verify that this works. But so if you have this, then you prove that the image of this projector is definitely contained in V. Or wait, no, sorry, you get the other way. So this implies that. The other inclusion is given by the fact that if you just look at the sum expansion, every element is in V. So this follows also from definition. And so, yeah, this therefore completes the proof that as long as V is finite dimensional, it is orthocomplemented as long as the global space is non-degenerate. And you also need V to be non-degenerate as well in order to get the projector. Okay. That concludes my thoughts on that topic. Do you have any questions? Okay. And so again, maybe a nice exercise would be to extract this logic and use it to prove the resolution of identity. I can conclude with some other remarks regarding non-degenerate spaces. So basically, I've established how non-degeneracy is very nice in that you can use it to construct orthonormal bases and prove the existence of orthogonal complements. Now, a first question that perhaps you could ask is, well, how strong of a constraint is non-degeneracy? And so we know, at least in the finite dimensional case, that you can construct an isomorphism to some space with a Graham operator, and the space is non-degenerate if the Graham operator is injective, which is not a huge constraint. Most operators are injective. But you can even go one step further and say that every space is isometric to a non-degenerate space. Isometric and not isomorphic. So what that means is that the isometry that maps you from an inner product space to a non-degenerate counterpart is not necessarily invertible. But if you somehow only care about things as modulo equivalence by isotropic vectors, then it's fine. Okay, so what I said in words, I can write on the board. So lemma, every inner product space is isometric to a non-degenerate one. True. Proceeds by explicit construction. This non-degenerate space, okay, let me give this a name. V is this quotient space. So this quotient space is defined as the set of all sets of this form. Let's see, so if I give you, say, V and V, it's the set of equivalence classes of this V, where the equivalence is defined by two elements being equivalent if you can relate them with an isotropic vector. So this is V plus X. So this set has a name. We'll call it V hat. And so the trick is to show that I can define an inner product on this space, which is going to be, and then that the inner product is going to be non-degenerate. Now, the first thing I need to clarify is that the zero element of this vector space is not the zero vector, because vectors aren't directly contained in here. Things that are contained in here are equivalence classes. So I'll just clarify that this zero is just V0. So then the next thing I need to do is establish an inner product. And it turns out you can do it like this. And this is well defined. So if I give you two different vectors, V and W, that have the same equivalence class, then this inner product will end up being identical. And this basically follows from the fact that if I give you, okay, actually, let's just quickly show that this is well defined. I can take some other U in V hat, which might not be equal to V. And then what I want to show is that UW equals VW. And I really only have to do this for one argument, because the other argument will just follow by the symmetry property of the inner product. So this is true if and only if V minus UW equals 0. But by definition of this, we know that V minus U is an isotropic vector. And we know that the isotropic vectors are the ones that are orthogonal to everything else in the space, so this works. So this is a well-defined inner product. And then the isometry that takes you from here to here is, so I guess I can say T is an isometry. Well, actually, I'll just say that the isometry is hat. So hat is the isometry because it preserves the inner product. And lastly, what I need to show is that this new space is non-degenerate. And so basically what that means, so suppose, let's say, I'll use capital letters to indicate elements of this guy. So suppose ST equals 0 for some S and for all T. Then what I can do is I can take a constituent vector of this guy. And then what that means is that for all constituent vectors of T, which I can generate every vector in the space this way, because I can just start with an arbitrary vector in the space and then construct the equivalence class. This guy will be equal to this inner product. And so what that means is there exists a V such that this inner product is always 0. What does that mean? That means that V is an isotropic vector, and what that means is that V hat is 0. Because I established the 0 vector is just this. So this completes the proof. Every inner product space is isometrically non-degenerate one. One more thing I can say. There's this nice statement. If I give you a semi-definite space, a semi-definite space is non-degenerate if and only if it's definite. I did want to specifically remark on this for the following reason, which is, so in this book by Gandhi, he provides a proof of this. His proof relies on the axiom of choice. Maybe he's trying to establish, like he's trying to prove the utility of some other lemma that he wrote on so-called maximal subspaces. And then pretty much anything that any subspace with the adjective maximal, you think of using Zorn's lemma to prove it. Zorn's lemma is equivalent to axiom of choice. So I wanted to show you a different proof that does not rely on axiom of choice. So the other proof, well, okay, I wrote the arrow in this vertical fashion, so I'll write it like this. Okay, so if we're in a semi-definite space, we know that the CSB, Cauchy-Schwarz inequality holds. And so basically what we're trying to do is show, so a definite space is one where there's no neutral vectors. And we're going to use the Cauchy-Schwarz inequality to show there's no neutral vectors. Suppose there was one. Okay, so suppose this, then by Cauchy-Schwarz, this inequality becomes true for all other vectors in the space, which I'll call it V. Therefore, V is isotropic because V is orthogonal to W for all W. Therefore, the space is degenerate, which is a contradiction. Or alternatively, I guess I should say, maybe not a contradiction, but if V is neutral, then it's isotropic, but we know that the set of all isotropic vectors in the non-degenerate case is 0. Okay, so this is one proof. This is maybe the easier direction of the proof. At least easier from the perspective of if I have this weapon, which is Cauchy-Schwarz, okay, I have a hammer, I apply the hammer to the problem, it solves the problem. So the other way you have to use maybe a different tool, maybe like a screwdriver instead of a hammer. The hammer doesn't work the other way. Okay, so the other way, which I guess would be up arrow. So to prove up arrow, I'm gonna do the contrapositive. Okay, so the contrapositive, what is the contrapositive of up arrow? That would be indefinite. Wait, hang on. So definite impl. Okay, so if definite implies semi-definite and non-degenerate, then I think we would have indefinite, because indefinite is the opposite of semi-definite. And degenerate. Yeah. Okay, so if I want to negate an and statement, that's equivalent to taking an or. So I have indefinite or degenerate. Implies, so not definite means there exist neutral vectors. Okay, so degenerate implying the existence of neutral vectors is easy, because in the degenerate case, we have an isotropic vector. So you have V isotropic, and an isotropic vector is necessarily neutral. So this is the easy case. So we got this part. So now what we can do is show that in an indefinite space, there exists a neutral vector. And we did this already. So that completes the proof. And this is significantly simpler than having to invoke axiom of choice. So this is all I had prepared for today. I know we have a couple minutes left. I don't know if you guys feel like I rushed anything, or perhaps I don't know. Like also for the people on Zoom, there's a lot of stuff that I wrote, and it's unclear how legible this stuff was. If there was like a section where maybe something wasn't so visible, I can repeat something. And if nothing else, we can continue next week. And then maybe there's a question of ordering the remaining topics. So I proposed a plan, which was next time we could start to define topology. I think we could define the weak topology and norm topologies on the space. And then after that, we can start to talk about the properties of operators that exist on the space. However, I was going over the kind of spectral properties and operator classes that I was looking at, and it seems like most of the theorems regarding those are on these things called crime spaces. And in a crime space, the topological structure is basically the direct sum of two Hilbert spaces. So it's relatively straightforward. So in terms of ordering, we could start to talk about maybe more practical things first. We could start talking about operators. And if we get to a point where I'm required to use topology, I can have like an intermission session. Or I could talk about topology first and then the operators second. So it's kind of up to you guys what you want to hear about.
The first choice that you said, like talk about more applications, and then if topology shows up, you...
Okay, yeah, sure. I can do things that way. Anything else? Let me check the chat window. I think we're good. Thanks.